Spoof surface Plasmon Polaritons waveguides have longitudinal and transverse electric fields with phase quadrature, implying that these electric fields along Spoof SSP waveguides have spin property. Based on the spin, orbit, and the action, we designed CP and LP Terahertz Leaky-Wave antennas.
Firstly, we investigated the spin property of the Terahertz SPP waveguide. These equations represent the propagating SPP fields. EX and EZ components have a 90-degree phase difference, as indicated in the simulated electric fields in the XY plane. The electric fields in the air around the SPP waveguide propagate along its length. EX and EY components also have a 90-degree phase difference, as illustrated by the simulated electric fields in the XY plane. Therefore, the SPP waveguide has spin electric fields in both XY and XY planes. The spin SPP fields can be coupled to generate CP radiation by loading the scatter based on spin-orbit interaction. Then, by introducing periodic elements, the confined SPP waves can be converted to Leaky-Wave radiation. We designed the DOCP, RHCP, and the elliptically polarized Leaky-Wave antennas, respectively. Two circular or elliptical radiations with opposite headings can generate a linearly polarized radiation. Therefore, we propose a Terahertz LP Leaky-Wave antenna. This antenna is conveniently fabricated by 3D printing, followed by a surface metallization process. The radiation patterns were measured by the far-field setup, where a pair of OML extenders from 140 to 220 GHz can enhance the VNA operating frequency to Terahertz band. The simulated and measured results are shown in these figures. This proposed Terahertz Leaky-Wave antenna achieves a high gain and large beam scanning range in the operating band. This work was conducted in the Static Laboratory of Terahertz and Millimeter Waves at City University of Hong Kong. For more detail, please refer to our paper. Thank you for watching.
In this video, a wideband and high-gain planar Endfire antenna based on Spoof surface Plasmon Polaritons at millimeter waveband is presented. Firstly, a unilaterally corrugated surface antenna is demonstrated to radiate Endfire beam tilted up from the flat plane of corrugated metal teeth due to the effect of finite ground plane. Then, to solve the problem of beam tilted up from the flat plane, ISSPPS Endfire antenna is designed with two symmetrically corrugated surfaces on the double sides of a metal strip. By analyzing the radiation performance of two symmetrically corrugated surfaces, we found that different current distributions will form different synthetic pattern. As mentioned above, the key factor to realize the Endfire beam with zero tilted angle is attributed to the identically normal electric fields and oppositely tangential components. Based on this conclusion, the feeding network is comprised by a T-shaped power divider and two-step impedance transitions from microstrip line to slot. Besides, to effectively excite the two identically normal electric fields along the two corrugated surfaces, two L-shaped slots with same direction are used and placed at the end of the transitions. By simulating the dispersion curve of the SSPPS unit cell, we chose an appropriate size, and we can find that the proposed SSPPS antenna has realized an Endfire beam with zero tilted angle. Finally, a novel planar end-fire antenna based on SSPPS at millimeter waveband is presented. By comparing the simulated and measured results of our proposed SSPPS antenna, this SSPPS antenna realized its unique performance in millimeter waveband. For more details, please read our published paper. Thanks for watching.
Hello, this is Sarkar, working as assistant professor at IIT Mandi, India. So one of my favorable topic is basically beam scanning antennas for 5G and upcoming 6G applications. And that's how in my current publication in IEEE transaction antenna propagation, I have presented a very unique approach to design the beam scanning antennas for azimuth plane beam scanning applications. To do so, the two things are there. I need to care about the feeding as well as the transmission line. Since the entire structure should be in the azimuth plane, so I need to use some kind of annular geometry for the feeding purpose as well as for the transmission line purpose. Here you can see the linear, the coplanar waveguiding structure has been turned into a curvilinear, the annular coplanar waveguiding structure for my application purpose or for my design purpose. Whereas also the transmission line, the entire linear transmission line, I have aimed the transmission line in such a way so that it can fit to the azimuth plane with the perturbation. Now for my design purpose, I have used the annular surface plasmonic theory for Polariton theory for my design. So this is very different from the usual transmission line. Since the vertical electric field usually we find for the transmission line is not present here. The electric field is basically in the horizontal plane and it transfers the energy in terms of the packet. So you don't require any ground plane for this kind of a design. So how you can design the antenna geometry then? So then after that, what I did, I put a very, very closely spaced radiating structure on the circumference of the transmission line that can probably provide the radiation pattern throughout the antenna geometry. This is the prediction. Now, how I implemented that? So I used the varactor diodes with a very close proximity with the transmission line and the radiating patch. And depending upon the capacitance changes with the varactor diode, the different electric field orientation or electric field concentration has been changed throughout the transmission line, which is really caused to have the radiation in a particular direction. If you can see for this case, suppose if the D7, all these diodes are turned on, the entire beam will be tilted in that direction. For this case, the second diode position has been turned on, so entire beam has been tilted in this direction. In such a way, you can have an entire azimuth plane beam coverage from this kind of a structure. And this is a fabricated prototype where the three varactor diodes are clearly visible here inside the structure. And that's how you can achieve a complete azimuth plane scanning beam coverage from such kind of a plasmonic structure-based media. So that's all from my side. And if you have later any discussion, you please write back to me to my email ID. I'll be happy to interact with you.